I've been asked to explain a bit better how one draws the actual gear teeth, and this is with reference to this 6-step process which you have in your notes and in the other gear video. Basically it boils down to drawing your base circle radius, which in our case is 140.95 millimeters, which is based on the pitch circle radius times cos of the pressure angle, so that's fine. And that's going to give us this circle. So we're going to set our compass to that radius and we're going to draw a circle like that. So that covers step one. We've drawn the base circle. Next is to make divisions, angular divisions. In the example on this page, I've used 10 degrees. But for best accuracy, one might want to go smaller than that. So this example here on the screen now is drawn at 5-degree intervals. So I started from the horizontal. You can start wherever you wish, and then make 5-degree increments between the lines. So from the center of the circle, construct a horizontal line. Obviously the radius is the base circle radius. This is drawn full size, or to whatever scale you choose. In this case it's full size. And then from that horizontal line, using a protractor, you're going to have to measure 5 degrees and draw the second line. Another 5 degrees, another line, and so on. So they are at 5-degree intervals. I picked an arbitrary number. I've drawn the original line plus another 1, 2, 3, 4, 5, 6, 7, 8 lines. The next step is to draw the tangents. Okay, now a number of you alarmingly don't know what tangents are, but a tangent is a line by definition that touches the edge of a circle only once. It doesn't cut that edge again. The red line is not a tangent to the black circle because yes, it cuts the edge over here, but it also cuts it again over there, so it's clearly not a tangent. The green line, on the other hand, is a tangent because it cuts the circle only in one place. Now in our case we have to have tangents drawn to this arc over here, the base circle, but these tangents must touch the base circle at these various ends of the lines. So if we pick one, for instance, this one over here, I'm going to place a ruler tangential to the circle and I'm going to draw a line, but most important is this must be 90 degrees. So what I would suggest you do is you take a set square and you place the set square on your page such that one edge is against the line and the 90-degree corner of the set square lays down here, and you're able to set up a perfect tangent. So here are all the tangents drawn to the various lines. This shortest one over here, or the first one should I say, its point of tangency is right here, and down goes the line. You can just see it there. You can extend it as long as you like if you wish. And obviously we have 90 degrees between this line and the line you've just drawn, such that it would then form a perfect tangent to the circle at this point. And then the second one, here it goes, here's the line, and the point of tangency is exactly there, and it is once again 90 degrees between the original line and the line you've just drawn, and so on. So there are all 8 tangential lines. The first one, and second one, third one, fourth one, etc. Next is to trim all of those lines to the lengths as per step 5. Now in this process here we were using 10 degrees. Remember, I'm using 5 degrees to get a little bit more accuracy. So the length of each curved segment is not 24.6, it's 12.3 millimeters. So the first line will be 12.3 millimeters long. The second will be double that, 24.6 millimeters. The next one will be a further 12.3 added to that. in other words 36.9 millimeters. The next one will be a further 12.3 added to that number, which will bring you to 49.2 millimeters, and you can carry on and add 12.3 to each one. And that would be 5 over 360, because it's 5 degrees times the full circumference, which is 2 pi base circle radius. So we've chosen 5 degrees, so 5 3/60ths is the portion of circle covered by your little piece, times the full circumference at 2 pi rb, and that's how we get to the 12.3 millimeters. So if we zoom right in, that first line we said must be 12.3 millimeters long. So from the point of tangency to its end point will be 12.3 millimeters. The next one is from its point of tangency, which is just off the screen here. It'll be, we said, 24.6 millimeters. The next one 36.9, the next one 49.2, etc., 61.5, and so on. So there we have the 8 points that we've drawn from the first line, the second line, etc., plus of course the original point, which is on the original horizontal line. And the shape of our gear tooth, this involute shape, is a spline or a curve drawn between those 9 points. Now on a CAD system you would use curve between points or a spline, depending which software you're working with. If you are working manually, you would use something like a flexi curve or a French curve, and you would draw the best curve you can between those points, and that would be the shape of your involute. Zoomed out a bit, that's what your overall picture is going to look like. Now remember, we're only going to use a small portion of this involute that we've drawn for our gear tooth. So to see which portion we're going to get rid of and which we're going to retain, we need to draw the various other bits of geometry, and I've started here with the pitch circle radius, which is 150 millimeters in our case. So compass on the center of the circle, and you're going to draw an arc of 150 radius, and that is what you see over here. So remember, that is an invisible line, you don't see it on the gear, but it is the diameter of the two imaginary circles, friction wheels, that roll together whilst this gear pair is going to be transmitting power. So there it is. And there's going to be a portion of tooth sticking above it, and there's going to be a portion of tooth sticking below it. Now to be able to finish this one off, we need to know how big the addendum is and the dedendum. Now we don't have any other information, so let's use the standard proportions that were given, where they suggest that you sometimes use addendum equal to module. And for this example, I'm going to use a module of 5. So with the module of 5 and the addendum equal to the module, it means that from the pitch circle we're going to extend 5 millimeters outwards to the end of the tooth. So we're going to discard all of this and retain this portion. Then the working depth, as you know, is twice the addendum, because the other tooth fits into this space over here and uses 5 millimeters of the involute. But for purposes of drawing, I think let's draw the dedendum, which is, if we use the standard proportions, 1.25 times 5. We're going to draw the lowest circle, 1.25 times 5 below the pitch circle. So 1.25 times 5 is 6.25. If we subtract that from the 150, which is the radius of this base circle, correction, of this pitch circle, we are going to get to 143.75 as the base of the tooth. So we're only going to use the portion from here to there, and we're going to discard the rest. So to summarize, we're going to have our pitch circle radius over there at 150. We're going to have radius to the addendum at 155. There it is there. And we're going to have radius to the dedendum at 143.75. And that is the portion of tooth that we are going to draw. Now, how many tooth does this gear have? Well, D equals MT. pitch circle diameter is equal to module times number of teeth. We know the pitch circle diameter is 300. We've elected to use a module of 5, so it follows that there are 60 teeth. So we've got to generate 60 of these spread around the circle. Now, so far we only have this one face of the gear tooth, and we need to know where to draw the other side of the gear tooth, which is a mirror image, but we've got to decide how far away to draw it. Now, in the notes, it concludes that the angle from a point on the pitch circle through one side of a gear tooth to the very same point on the next gear tooth must be 360 degrees divided by the number of teeth. So that's the circular pitch basically. Now, remembering that a tooth from the other gear has to occupy the space in between, our gear had better leave a corresponding size space for that other gear tooth to fit in. So it follows that the distance, the angular distance from this dot to that dot is not 360 over t, but half of that. In other words, 360 over 2t. So 360 over 2t gives us 3 degrees. From the blue line to this black line over here would be 3 degrees. But for purposes of drawing the other side of the gear tooth, we need to mirror this side around a mirror axis to get it to be a mirror image in the correct place. And we're going to have to further halve that 3 degrees, in other words to a degree and a half, 1.5 degrees, and generate a line from the center of the circle out at 1.5 degrees. And then we can fold the piece of paper around that line, or if you're in a CAD system, you could obviously use the mirror function to generate this other side of the gear tooth. Zooming out a bit, this is what the bigger picture would look like. So from a point on the pitch circle, we draw the first line, and we know that 360 over 2t would be the angle to the line that passes through that point, and half of that, as said, was 1.5 degrees, and that's going to allow us to draw the other side of the gear tooth in the correct position. And once you have the full tooth drawn correctly, you can now make 59 further copies spread around the circle at the correct angle to fit in all 60 teeth in total around your gear. And that is what your gear would look like with all 60 teeth drawn. Obviously that's a very tedious process on a piece of paper, in other words manually. So I would only ask you to draw 1 or 2 or maybe 3 teeth, but you wouldn't have to draw all of them because it would be very tedious. If you're in a CAD system, obviously very easy, you simply do a polar array and you can draw all the teeth